Hello, please, good evening. Can you hear me?
Yes, please.
All right, please, sorry for the delay. Okay, so today we will solve some examples on Unit 2. Then we will continue with Unit 3. We'll look at the step up, step down, and then the boost back on later. That is what we are going to look at. So we will solve an example, then we move to that. Okay, so this is question we have. It's quite lengthy, so I will want you to pay attention. So I'll let you write all the details down, then we will solve it together. Okay. So it's just one question that we will look at, which is slightly different from the one in the slide. So we will do, we'll calculate for average values of current. We will calculate for losses, power losses, the switching, conduction loss. We will do thermal modeling. That is basically what this question is about. So let's go through the question. So the question says a step up converter is used to regulate the DC input voltage from a photovoltaic panel. The converter is built using a fast switching IGBT and diode. So both with negligible tail current. So the IGBT has no tail current, and the diode has no recovery current. So full load steady state current waveforms of IGBT and diodes are shown below. So okay. So let's take note of the waveform. So this is the waveform. So some of the things are not clear, so I'll try to write them out. So this is zero. Oh, sorry. Let me change the picking there. Okay. So I'm coming. Please coming. Okay. So let's continue. So the minimum current is 3 amps. So this is 3 amps, and the maximum current is 7 amps. So this is 0.7 T, and then this side is 0.3 T. So take note of this. So this waveform is for the IGBT, and then this waveform is for the diode. So please take note of the waveform so you can draw it or write out the value. So similarly, the minimum current here is 3 amps, and then the maximum is 7 amps. So that is the preamble we are giving. So take note of the waveform. So we'll come back to them. Okay. The first part of the question says the IGBT threshold voltage and its equivalent impedance capacitance is 10 nanofarad. The gate drive voltage is from 0 to 15 volts. The first question says we should calculate the minimum value of the gate resistance required to ensure that the peak gate current is less than 3 amps. With this value of gate resistance, calculate the power loss in the gate resistance, assuming that the RMS gate current is 0.1 amps, and also the time it takes for the gate source voltage to reach the threshold value. So this is the first question we will solve. So let me see if we can. Okay, I just want to get a space. So I'll always come back to the question. So I just want to get a space, right? Okay. Okay.
Let me ask something. Can he hear?
So okay, so let's take note of the information. So we are told that first of all, we are supposed to calculate the minimum gauge resistance. So the minimum gauge resistance, we know that resistance is given by as what? Resistance is voltage over current, right? So we've been given the gauge drive voltage. So gauge drive is from 0 to 15 volts. And then we are told that the current that is the Imax, should I think it should not be less than or so. So I think it should be less than 3 amps, right? So the maximum current should be 3 amps. So the resistance we are calculating with the minimum. So what we need is the voltage is changing from 0 to 15, right? You said you can't hear me. Okay, please, I'm coming.
You said?
You can't. I'm coming.
I said I can't hear him.
Please, she said you can't hear me. Please, can you hear me now?
Yeah, using the Wi-Fi. No, I bought it.
Please, I'm not getting what you're saying. Please, am I audible?
Hey, what is happening to my laptop? I don't understand. Because I can't hear anything.
But please, can I be heard? I just want to be sure.
Hello, yeah, please, you can be heard.
All right. Let's continue. Okay, so as I was saying, we need the minimum resistance. So the voltage drive is from 0 to 5 volts, right? So if you calculate the voltage range, the difference is going to be 50. So our R G min will be equal to the difference in the voltage, which is 50 minus 0. Minus 0 divided by the minimum current, which is 3 amps. So this gives us 5 ohms, right? So the minimum resistance should be 5 ohms. So from the question, so we are told that the maximum current should be 3, and then we know the drive voltage range, so we can calculate the voltage difference, and that gives us the resistance. So the minimum resistance should be 5 ohms. All
Why
right.
they mute my mic?
And we are also asked to calculate the gauge loss. So which is PG loss. So we've been given the RMS current. So the IG RMS to be 0.1 amps. So that is what we are giving. So we know that anytime we have resistance and we have to calculate power loss, it's given by R G times what? IG. It will be given by this expression, RMS squared, right? So that is what we are going to have. So we go ahead and calculate for the loss. So we have 5 times 0.1 squared. So please, if you have your calculator, you can punch and then help me with the value. But I'm expecting you to get 0.05 watt. So this is going to be the gate power loss. So from the values that we are giving. Please, if you don't understand anything at any point, please draw my attention so that I'll take my time and explain. So in case you get a similar question in your midterm, you should be able to do it. Okay, so this is the second part of the question, right? So we are also asked to calculate the time. Please let me let me come back to the question. So when you come back to the question, the question says we should calculate the time it takes for the gate voltage, the gate source voltage to reach the threshold voltage. So we've been given the gate capacitance, right? So anytime you have a capacitor and you connect a voltage source to it, it takes time for the capacitor to charge. So the voltage will rise from 0 up to the maximum value when it's fully charged. So capacitors doesn't allow voltage to change that much. So we have to get the charging voltage of a capacitor and then discharge voltage of the capacitor. But since we are focusing on the charging voltage of a capacitor, then we have to use that one, right? Okay,
When you're
so we
reading much, you
come.
realize that I'm still on the bed. Wow.
All right. So that means we need to calculate for the the charging capacity voltage of a capacitor. So if you've done transient analysis, I'm expecting you to know this formula. You remember there is a formula like this, which is giving 1 minus E exponent T over RC for a capacitor. So this is the charging voltage, and the discharging voltage is given by V naught E exponent TRC. So this is the formula that we are going to use. Since the is charging the gate capacitance, then we have to use the first one. So realize that in steady state, the voltage that will be there is going to be the maximum voltage of the supply, so which is 15 volts. So V naught is equal to 15 volts. That will be in steady state. So when it's fully charged, it will charge to V naught, which is the maximum voltage. So we need to get the time constant. The time constant tau is given as RC. So we've calculated for the minimum resistance, which is 5 ohms. So we've also been given the capacitance too. So we have to calculate the time constant. So the time constant will be given by 5 times 10 times 10 exponent minus 9, because the capacitance was given as 10 nanofarad. So this gives us the time constant, which is going to be 5 times 10 exponent minus 8. So this is our the time constant, right? So we are told that the capacitor, the voltage will rise up to the threshold voltage. So the threshold voltage is 5. So which is so it has to rise from 0 up to 5. So this V of t is the 5 volt. So we have everything here to help us with the calculation. So we substitute the value. So we'll have 5 to be equal to 15 into 1 minus e exponent t over the time constant. So let me still keep it RC so that when we make t the subject, then we'll come and substitute it, right? So this one you can expand and simplify, right? So you're going to get 5 to be equal to 50 minus 15 e exponent minus t over RC. So we can make this the subject, right? So if you do that, you're going to get 15 e minus exponent minus t RC to be equal to 15 minus 5. So you can divide through by 15, right? So that gives you e exponent minus t over RC to be equal to, sorry, this is 5, to be equal to 10 over 15, and this is 2 over 3. So we can apply anti-lock on both sides. So when you do anti-lock on both sides, you're going to get minus t RC to be equal to ln of 2 over 3, right? So you have minus t to be equal to RC ln of 2 over 3. Then you can make t the subject. T is equal to minus RC ln of 2 over 3. So we can now do the substitution. So you have 5 times 10 exponents minus 8 multiply by, sorry, don't forget the minus sign, multiply by ln of 2 over 3. So you realize that when you have a logarithmic function, anytime the value is less than 1, you are expecting a negative value. So this will simplify to a negative value, which will cancel this, and we'll end up with a positive value. So please, if you have a calculator, I would like you to punch this and then give me the answer. So please, let's make it interactive. We are solving questions, so ask questions and also answer
Hello.
questions. So yes, hello.
Hello.
Yes, please, I
Please,
can hear
after
you.
the PG laws, everything you're writing, I'm not seeing it. I don't know why.
Please.
I could see you.
I'm also not
but
seeing
then I'm not
anything. I
seeing
thought I was the
anything.
only one.
Oh, probably. I'm not sharing that part. I'm coming in.
Yes. So you'd kindly have to go back. Yeah, thank you.
But can you see my screen too?
Yes, I can see it now.
Oh, okay.
Yes.
So okay, let me project it again and see whether you can see. Can you see what can you see it now?
Currently, I can see everything that you have written. I can see it now.
Oh, okay. I
Yes.
will go over everything. I will just explain so that you can get it. Okay. So the question says we should calculate the time it takes for the voltage to rise up to the gate voltage to rise up to the threshold voltage. And you know that at the gate, so IGBT, this is IGBT, right? And there is a gate. So this forms some capacitance, and the value was given as 10 nanofarad. So you realize that
Please,
there is.
I cannot see what you are writing at all.
Okay. Okay, let me write it here. So if you can see, so we have. Can you see what I'm doing now?
No, I don't know whether I'm the
No,
only
please.
one.
Oh, wow. then it's going to be a little. Okay, I'm coming. Hey. Okay, but can you see the question? I want to know if you can see the question. The page I'm showing now. Please, I'm asking, can you see what I'm showing now? Hello, please. Can you
Yeah,
can you guys
yeah.
hear?
I think is the question, right?
Yes.
Okay, I can see the question.
I can
Okay.
also see the question.
Okay. So let me come to. Can you see the what I'm showing now?
Yes.
Wow. But if I go into this is PPT. So if I go into presentation mode, I think it doesn't. Most of you cannot see. But I think there is no space on this one. This side is for me to write. So I don't know. Okay. So what I'll do is I will I'm not on your page, so I will send the question to Randy, then he will share it on your page so that I will only project what I'm writing so that you will look at the question from your end so that you can solve it. I hope that's fine. Please give me some minutes. I'm coming. So if you have if you get the question, please let me know so that I'll reshare my screen again for us to see. Okay.
Um, I think we have it now.
All right. Okay then. I will only share the PowerPoints where I was writing. Then we will continue from there. So if you can see my screen, let me know. Please, I hope you can see what I'm sharing.
Yes, please.
Okay, sure. So let me take it again. So this is what we have. This diagram we have here represents the IGBT. So the IGBT, the gate is gauge controlled, right? So this is the gauge resistance, and then we have a gate voltage connected to it, and there is a capacitance at the gate. So that capacitance was given as 10 nanofarad. So realize that you have to keep increasing the when you supply the gate voltage, right, which is the maximum gate voltage, right? So if this is at 15 volt, and we are told that the threshold voltage is 5, so how long will it take for the capacitance voltage to increase from 0 to 5 volts? That is what we are looking at, the time we are looking at. So it's the charging time of this capacitance. So when it gets to 5 volt, that is when the gate, the IGBT will now be turned on, right? Because that's the threshold voltage. So we want to see how long it will take for the IGBT to turn on. So since there is a capacitance, we need to look at the charging voltage of the capacitance. So I wrote two formulas here. So the first one, let me change the color so that you can see what. Okay, the first one, right? This one. So this is this one. This is a charging capacitance of a capacitor. Sorry, charging voltage. And this one, the one below here, is the discharging voltage, right? So since we are looking at the charging, we will pick the first one. So this V naught is a steady state value. So when everything settles, what will be the voltage across the capacitor for a very long time? So realize that when you give it some time, it will charge up to the maximum voltage. So the maximum voltage that is applied to the gate is what? 15 volts, right? So because it's 15 volts, V naught is going to be 15 volts. And then the voltage we are looking at is 5 volts, right? So V
Please,
of
am
T
I
will
the
be
only
equal.
one who can see this writing?
Okay, I'm not writing, I'm actually talking.
Okay.
Yes. So V of T is the 5 volts we are looking at. So V of T will be 5 volts. V naught will be 15 because that is the steady state voltage. The next thing we need to calculate for is the time constant, which is given by RC. RC is the time constant. So we've calculated for the minimum resistance, which is 5 ohms, and the junction capacitance, the gate capacitance was given as 10 nanofarad. So when we multiply the resistance by the capacitance, that gives us the time constant. So we have 5 multiplied by 10 times 10 exponent minus 9. So this gives us a time constant, which is equal to 5 times 10 exponent minus 8. So we do the substitution, right, into this equation. That is the one at the top. V of T equals to V naught into 1 minus E exponent minus E over RC. That is the one we are going to use. So when we do the substitution, so let me just okay, let me erase what I've written. Oh, I think I cannot erase it. Okay, but let's continue. So you have 5 to be equal to 15
This type of
into 1.
questions, are they likely to draw?
These questions.
Yeah, like the things that you are doing, are they likely to drop? Because they seem like abstract or
It can come.
okay, sure. Is it going to be theory or MCQ?
Professor does theory, but he might give you some MCQs, maybe about 5 or 7 MCQs to do, but most of the questions will be theory. So if he's going to set
Okay.
questions, definitely there will be some question on thermal monthly. Right. So this one
Okay,
we're just
sure.
focusing of the gates of the IGBT. So it's
Okay,
possible he
okay,
can give you a question like that.
okay.
Okay, all right. So now we do the substitution. We make T the subject, right? That is what I went through. So if you expand this expression, when you expand it, you have 15 to be 5 to be equal to 15 minus 15 E exponent T over RC. So we try to make T the subject, right? So you make E of T the subject, take lane on both sides. So when we do that, you arrive at this one. This should be the final when you make T the subject from here. That is what you will arrive at. Then you substitute RC. So I was explaining that you see the lane of log of a value less than 1, right? A value less than 1 will yield a negative value. So because of that, this term will give us a negative value. So which will multiply this negative. So at the end of the day, you end up with a positive time. So that was what I was saying you should calculate. So you get minus 5 times 10 exponent minus 8 multiplied by lane of 2 and 3. So I would like you to do that calculation and then give me the value. So please, do you understand what I did now? Okay. So please, who is done?
Is it 5 by 10 per negative 8?
Yes.
Okay, then it's
I had mine
2.027.
2.0
027.
027
minus
7.
2.027.
times 10 exponent
Negative 8.
negative 8. Right.
Yeah,
Okay.
yeah.
All right. So this should be in seconds. So you can that is what you will get. As this is the time it to take for the for the IGBT to turn on. So for the voltage to rise up to the threshold voltage before it can turn on. So that is the A part of the question. It was just focusing on the gate. So now let's look at the next question. So the B part says we should calculate the average and RMS values of IQ and then the average value of ID. So please take note of the waveform. So when you look at the waveform, we need in calculating average, we need duty cycle, right? So we need to calculate the duty cycle. So we need to get the T on. So we know that T on is equal to duty cycle times T. So the duty cycle will be given by T on over T. So when you look at the waveform, the T on the T on is the time that the IGBT is on. So when you look at the waveform, it's going to be 0.3 T. That is the time the IGBT is on, right? Some of you, if you don't look take care, you might pick the 0.7. So please be careful. Look at the understand the waveform before you pick your duty cycle. Some of you, most of the times, it's like the duty cycle comes before, like the T on usually comes before the T, or by this time the positions has been interchanged. So you have to take note. So we will have T on to be 0.3 T over T. So this gives us 0.3. So this is our duty cycle. So now that we know the duty cycle, the next is to calculate the average value of IQ. So IQ average, we know that these are standard waveforms, and we know the expressions for them already. So it's given by A over B, A plus B divided by 2, multiplied by the duty cycle. So A is the minimum current, B is the maximum current. So from the waveform, we know that the minimum is 5 amps, the maximum is 3. Please, sorry, it's 3 amps, and then the maximum is 7. Right? So we divide this by 2 and multiply by 0.3. So you have 10 divided by 2 times 0.3. So this is to give us what? 1.5 amps. So this is IQ average. Please, is it clear? You are not seeing anything.
We are not seeing it. Yeah.
Which page are you? What are you seeing now? This is going to be rich. Can you see my screen now?
No, it's
Yes,
stuck on
yes,
that
we
one.
can.
Please, can you see my screen now?
If you are not
Hello.
writing anything, then yes, we can.
All right. So, okay, I'm coming. Can you see what I'm writing now? Okay. I'm coming. Let me see. Okay, so what I was saying is we've calculated for the duty cycle, right? Which was 0.3. Can you see what I'm writing? Then we are supposed to calculate IQ
Yes,
average.
we can. We can see it.
Okay, then let's just go with this. I think this should be fine. Okay, so I average is given by the minimum plus the maximum current divided by 2 multiplied by the duty cycle. So we know the minimum current to be 3, maximum to be 7. So we divide that by 2 multiply by 0.3, right? So I think if you simplify, you end up with 1.5 amps. This is IQ average. So we calculate the RMS. So IQ RMS is given by square root of duty cycle over 3 into A squared plus B squared plus AB, right? This is the formula we were given. So we just use it. So you have 0.3 divided by 3 into 3 squared plus 7 squared plus 3 times 7. So this will be the RMS value. So please, I think this one you should solve it and then give me a value.
2.81.
2.81, right? Amps. So we've gotten IQ RMS. So the next thing we are supposed to calculate is the ID average, right? So I move to the next slide. Can you see the next slide now? Can you see?
Yes, yes.
Yes.
Okay. So we will have ID average to be A plus B over 2 multiplied by 1 minus duty cycle. So we do the substitution. You have 3 plus 7 over 2, 1 minus 0.3. So this one will be 0.7 times 5. So that will be 3.5 amps. So we are done answering the B part of the question. So we've calculated the average and RMS value of IQ, and we've also calculated the average value of ID. So that answers the B part of the question, right? All right. So we go to the C part of the question. Says that in the component data sheet, the following information is found. The first information is for positive temperatures, the IGBT on state resistance is given by R on equals to 0.05 plus 0.002 T. So R on
in the cloud
is 0.05 plus 0.002 T. So where T indicates temperature in degree Celsius. That is the first information. The second information is the IGBT and diode on-state voltage drop is 0.6 volts at 20 degrees Celsius. So voltage drop, let me just say V
initially in Portugal
is 0.6 at 20 degrees Celsius and decreases at 2 millivolts per degree Celsius. The diode's resistance can be assumed to be negligible. So we are told that this voltage decreases at the rate of 2 millivolts per degree Celsius. Assuming an operating junction temperature of 90 degrees Celsius, calculate the conduction power losses in the IGBT and in the diode. So this is the information we are giving. So this is the information from the data sheet, right? So the IGBT on state resistance is given by this expression, which depends on temperature. So it increases with temperature, and the voltage drop decreases with temperature, right? So that means that we need, and we have to calculate the resistance. So if you look at the IGBT, its model has on-state resistance and a certain voltage, right? So we are told that this is R on and this is, let's say, VD, so the voltage drop. So this R on changes with temperature, the VD also changes with temperature. So this is the on-state model of the IGBT. So if you are to calculate for the power loss of the IGBT will be equal to IQ average times VG, which is already an average value, plus IQ
Hello,
RMS
please, we
squared.
can't see what you are writing.
You can't see what I'm writing.
You can see.
Yes.
Yeah, I can see you.
Yeah, I
Okay.
can see. So try refreshing your browser.
Okay, so multiply by R on. So this is what we are going to get. So we need to get the R on at the 90 degrees, the temperature of the temperature given was 90 degrees, right? So we need to get the R on at 90, and then the VD, that is the on-state voltage drop at 90 degrees. So that is what we need to do. So first of all, let's calculate for the R on at 90 degrees. So R on at 90 degrees, we just substitute wherever we see T, we will put 90 there. So you're going to have 0.05 plus 0.002 multiplied by 90. So this gives us R on. So we'll have 0.05 plus, please, you can just punch your calculator and give me the final answer so that I will know.
And please, where are we getting the 90 from?
Okay, so from the question, it says assuming that I'm coming. So it's from the question that we are giving that value. So it says assuming an operating junction temperature of 90 degrees Celsius, calculate the conduction power losses in the IGBT and in the diode. So the operating temperature is 90, but these values, we are told that R changes with temperature, right? So if it's at 90, if you are looking at the temperature of 90 degrees, the R, so we need to get the R on at that temperature. So we have to substitute T with 90. Please, do you get it?
Yes, please. Thank you.
All right. Okay, so who is done calculating the value of R on?
0.23.
0.23 ohms. So that is R on. So we need to also get this, the voltage drop at 90, because what we are giving here is the voltage drop at 20 degrees Celsius. So we need to get the voltage drop at 90. So I will move to the next slide. So if you can't see it, please let me know. Can you see the next slide? Okay.
Yeah.
So we have 0.6 at 20 degrees Celsius. So what is the new VD at 90 degrees Celsius? So we are told that it's decreasing, right? So if you are to draw it like a graph of VD against temperature, it's going to be dropping like this. So at 20, you're going to get 0.6. So at 90, what are you going to get? This is what we are trying to calculate for. We are told that the slope is what? 2 millivolts per degree Celsius. So what you just need to do is, so this is just very easy to do when you have this one model, right? So what we are going to have is why that is, if we take this as our first value and then this as the second value, then we are going to have VG minus 0.6 over 90 minus 20 to be equal to 2 times 10 exponent minus 3, right? So when you make VD the subject, you're going to get 0.6 plus 90 minus 20 is 70, right? 70 times 2 multiplied by 10 to the power 3. So, sorry, is it plus? Sorry, this is negative. Sorry, sorry. So it will end up with, we will get a negative value. So the slope is negative because it's decreasing. So you get a negative value. Please, who has a question on this? Any question? So if you don't have any question, I'm expecting you to get 0.46 volts as the new voltage drop at 90 degrees Celsius. Please, do we all understand this? Hello.
Yeah.
All right. So now that we've gotten our R on and then VD, that's the voltage, forward voltage, the onset voltage, we can go ahead and calculate for the P loss. This is for we are doing this for the IGBT. So we are going to have 0.46 multiplied by the average value of the average current of what? The average current of the IGBT, which was 1.5. So we'll have 1.5 plus the R on was 2.3 times the RMS current. The RMS current is given by 2.81. So we square that, and that gives us the conduction power loss of the IGBT. So if you have any question, you can ask before we move on to the diode. Please, I hope you are following.
Yeah.
Okay. Please, I hope what I've done so far is right. The values that I've written here. Okay, so what is the total power loss now?
2.506 watts.
Okay, so this is the for the IGBT. So we look at the diode. So the diode, when you go back to the question, the diode we asked to neglect its series resistance and just focus on the voltage drop, right? But when you look at it, its forward voltage drop is the same is the same model as the IGBT. So that means that the VD that we calculated for the value, this value that we got here, will be the same for the diode, right? So it will be the same for the diode. So we just use that to calculate for the diode on power loss. So VD loss, so this is for diode, will be equal to ID times ID average. So this is 0.46 multiplied by the average current of the diode, which is 3.5 amps. So this will be the conduction loss of the diode. So what are you getting? Are you getting 1.61 watt? Please, are we all getting this? Okay, so that is the C part of the question. You go to the D. So the D part is in the component data sheets, the following information is found. The MOSFET junction to case thermal resistance is 1 degree Celsius per watt. The diode junction to thermal resistance, junction to case thermal resistance is 2 degrees Celsius per watt. The heat sink to ambient thermal resistance is 0.45 degrees Celsius per watt. That is the information then. The IGBT turn on and turn off voltage, energy is 0.4 joules and 0.04 joule, millijoules rather, and 0.06 millijoules respectively. the diode switching losses are negligible. In constructing the circuit, the IGBT and the diode are physically mounted on the same heatsink. So the first part of the question says, draw the equivalent thermal model for the arrangement. And the second one says, in the application, the ambient temperature must be as high as 40 degrees Celsius. Determine the minimum case to heatsink thermal resistance that must be accepted to ensure that the junction temperature of neither devices exceeds 90 degrees Celsius for a switching frequency of 25 kilohertz. All right, so the question is quite lengthy. So let's just summarize the information. Okay. All right, so let's just summarize the information. Okay, so let me summarize that information here. Okay, so we are told that for the IGBT, which is the MOSFET, we are told that the RJ2 case is 1 degree Celsius per watt. This is, let me qualify it by adding Q so that we know that it's for the IGBT. Then RD, which is for the diode junction to case, is 2 degrees Celsius per watt. We are also told that the R heat sink, right? So H to ambient, so heat sink to ambient, so that is the HA here, is given by 0.45 degrees Celsius per watt. So this is what we are given about the thermal resistance. We've also been told that E on is given as 0.04 millijoules and E off is given by 0.06 millijoules. So we are asked to neglect the switching loss of the diode. And the switching frequency, that is Fs, is given as 25 kilohertz. And the first question says we should draw the thermal model of the thermal model. So we are told that both devices, the diodes and then the IGBT, are physically mounted on the same heatsink, right? So we need to get the thermal model. So the thermal model, first of all, there will be a resistance between the junction and the case of both devices. So we'll first of all have a resistance, junction, and case. So if this side, I'll do it side by side. So one is for this side, the left side is for the IGBT and the right side is for the diode. So we'll have junction to case. So this one is 2 degrees Celsius per watt, and this is 1 degree Celsius per watt. Then there will also be a resistance between the the case and then the heat sink. So there is a resistance here, and there is also a resistance here. So this is heat sink, this is heat sink. But because they are physically connected to the same heat sink, we have to join this one and that together, right? And there will also be a resistance between the heat sink and then the ambient. So we'll have a resistance like this so this will be the ambient, right? So that is the thermal model. But because we want it to be like an electrical circuit, then we need to complete it. So in completing it, we need to get we know that is the power loss is what generates the heat. So that heat has to flow. So the heat that we are trying to take out is from the power loss, right? So the power loss is what is generating the heat. So we will, because the heat needs to flow, we will treat it like current. So we have the power loss, which is like current, connected like this, so that we can get a complete circuit. So we'll have a similar one on this side.
I can't hear you. Am I the only one?
Me too. Fine. Oh.
It's Randy here. Randy.
Ah, I think he has left. Randy, yeah, your power electronics. I cut you. Yeah, I think you have left the meeting then. I'm not reaching. Okay, so Sinaderi says he's having some network challenges, so we should hold tight. He'll be back.
Okay, hello, please, can you hear me? Can you see my screen as well?
Yeah.
Okay, so this is the thermal model, but we are not done, right? So we go back to the question and then get other stuff and then come up. So when you look at the question, we've been given the temperature. So we are told that we should ensure that the junction temperature of neither devices exceeds 90 degrees Celsius. So the junction temperature here is 90 degrees Celsius. And the one at the diode side too will also be 90 degrees Celsius. So the ambient is at 40 degrees Celsius. So what we have here is the thermal model. But you realize that the power losses, we still don't know them yet. So the next task is to now calculate for the power losses, the total power loss in IGBT and the total power loss in the BJT. So we know that we have three different power losses. That is the on-state power loss, the switching power loss, and then the off-state power loss. So in this example, nothing has been said about the off-state power loss. So we just forget about that one. And we focus on the on-state and then the switching loss. So for the IGBT, we know the on-state power loss. We just calculated it, right? Then the next information we need is the switching loss. So we've been given enough information to help us calculate the switching loss of the IGBT. So let's do the IGBT first, then we'll do the diodes. So for IGBT, we need to know the total loss is the on-state loss plus the switching loss, right? So the on-state loss, let me go back to where we did the calculation. I think it's here. So the on-state power loss is 2.506 watt. So that is the on-state power loss. So we have 2.5606 watt. So the next information we need is the switching loss, right? So we know that the switching loss, E switching is given by E on plus E off multiplied by the switching frequency, right? So how many of us remember this formula? He gave about three
I remember.
formulas. So this is one of them. So we need to do the substitution. So we are going to have 0.04 plus 0.06 times 10 exponent minus 3 multiplied by 25 times 10 exponent 3. So this gives us the switching loss of the IGBT, right? So we have 0.1 times 25. So are you getting 2.5 watt? If you simplify this, so that will be 2.5. So we are expected to get 5.006 watts as the total power loss in the IGBT. So please do the calculation and confirm what I've done. So the next is the diode. So the diode, we are asked to neglect the switching loss. So it's just the conduction loss. So we've calculated for the conduction loss already. So let's go back and then check. This is the conduction loss of the diode, which is given by 1.6 watts. So we'll have 1.61 watt. So we come to the model and then write the values there, right? So we know the power loss in the diodes and then in the IGBT. So that gives us a complete thermal model. Please, is that clear? Okay. So now that we have our thermal model, the second part of the question says we should determine the junction. I think case to, let me confirm that. Determine the case to heat sink thermal resistance that can be accepted to ensure that the junction temperature of neither device exceeds 90 degrees Celsius. So we are interested in the junction phase, sorry, the case heat sink thermal resistance. That is what we are interested in, right? So R theta, that is CH, of both devices. So R theta CH. So of both devices. So that is what we need to do. Okay. So this is where, because this now looks like an electrical circuit, we need to start applying our electrical circuit principles. So you've already been told that temperature is like voltage, power loss is like current, and the resistance behaves like resistance. So that is what we are going to apply. So this is what we don't know, and we are trying to calculate. So we can begin to take loops, right? So we can begin to take loop. So if I take a loop from here to here, that is on the IGBT side. So if I move here now to here, take a loop like this, right? What would be the equation? So we know that temperature is like voltage, right? So that means that at this point, I have a certain potential at the junction. There is a certain potential at this point. So the difference gives me the drops in the resistor. So that is the idea I'll be applying. So I'll write it on the next slide. So here. So I'm going to have TJ. So TQJ, which is the IGBT side, minus T ambient should be equal to all the drops. So let's go back to here. So you realize that the power that is flowing through can you see the cursor? I don't want to. Can you see my cursor? All right. So we know that this resistance and then that resistance are in series. So we have the power loss in the IGBT flowing through both. But when you come to this resistance, the heat sink, the case heat sink to ambient resistance, you have both the power loss in the IGBT and the diode flowing through it. So we can use that to write an equation. So we will have PQ loss into RQJC. This is for the, and then RQCH plus the one through the heat sink. So which will be RHE plus the power loss PQ loss plus PG loss, right? So we can, this is the expression you can get. So we start substituting in the values. So you have 90 minus 40 to be equal to PQ loss is given by 5.006. We know this is 1. This one is what we don't know. So we just keep it. Sorry, 8 plus this one is, we know it to be 0.45, right? And then this is 0.005. Sorry, this is a 0.6 plus 1.61. So the only unknown is what? RQCH. So that is what we are going to solve for. So that is how you go about it. So you can see that similarly, we can write equation for the diode side and also determine it. So that is how you go about solving this example. So let's just complete it. Let's make this a subject. So this side will have 50 minus I think 0.45 times this plus that. So you can just punch your calculator and then help me with the value so that it reduces the things I write. So So we just make it as a we get 1 point, 1 plus RQCH to be equal to 50 minus 2.7977 divided by 5.006. So, okay, let me just make it the subject. Let me make it the subject straight away from here. So you just get this minus 1, and that gives you the value. So you can punch that for me. I hope you are following. I don't want to be the only one talking.
$8.39.
So you get 8.392 per watt.
Oh.
So that is for the IGBT side. So we look at the diode side. So you can also write a similar equation, right? So what I'll just do is I'll just go and look at the one we have and then make substitutions, right, for the diode side. So the diode side, let me write it so that we all can see. So we'll have T DJ minus TA, right? PD loss time this one multiplied by the series thermal resistances, junction to case and case to heat sink. So you have 2 plus RDCH to be equal to the sum plus what? The sum of the power losses. So you get 0.4. Okay, let me just leave it. 0.45 the power losses, right? So PD loss plus PQ loss. So you are going to get something like this. So you substitute in the values and make this a subject, right? So you have 90 minus 40 to be equal to 1.65, 61, 2 plus RDCH plus 0.45, 1.61 plus 5.006. So I'm expecting you to get, when you do the simplification, sorry, this should be D. CH, I'm expecting you to get 50 minus 2.9772 divided by 1.61 minus 2. So I'm expecting you to get this expression. So do the
You get
substitution and let me know.
27.21.
2.1.
Yeah, degrees Celsius per watt.
So that is how you go about solving this example, right? So we are done solving the example. So if you have any question, please, you can ask. So you realize that this one is different from the one in the slide, right? So though the idea is similar, but the way the question was framed is different from the one you saw in the slide. So let me make this clear. So you realize that in this particular example, the E on loss and then E off loss were giving, energy were given to us. I mean, in your example, he can let you calculate for these values. So go and learn how to calculate for them. So the question you can just change the information given. You see this one, he gave you the waveforms. He can give you the circuit diagram, ask you to draw the waveforms yourself, calculate for the minimum current, calculate for the maximum, calculate for the duty cycle. He can give you any information. So what you need to do is make sure you understand how to do all these calculations, right? So you can bring a similar question. You just change the parameters or change the whole question, but it's still testing the same concept. So this is the example we have to solve. So if you have any question, you can ask. If there is no question, then I think we still have a few minutes. If you will permit me to explain little on the DC to DC converter. So we just analyze either the step up or step down, one of them, then we'll end today's class. I hope I'm permitted to continue. Please, can you hear me?
Yeah, you can.
All right. Okay, so let's just go through the choppers. So this one we are focusing on choppers. So I'll try and skip the reading part so that we can get to the analysis. So all these, I think you can go and read. So the this is what we will focus on. So we just focus on the choppers. So let me just move straight to the choppers. So step down. So let's start with this one. So I'll just okay. So the first thing we are looking at is step down. So I know we all understand step down. So step down, it basically steps down the voltage. So it takes a DC voltage and reduces it to a lower value for you. So this is basically the circuit. So we are looking at the one with resistive load. So we are told that a power electronic device, we have switches, storage elements, right? So let's analyze this particular one. It's very simple, but you need to understand it. So here we have a switch connected between the load, which is a resistive load, and the supply. So we are interested in the output voltage and the output current. Then after that, we'll calculate for the average current and the average voltage. Get our duty cycle. That is what we are focusing on. So let's analyze what is happening. So when the switch is closed, so when it's closed, this is shorted, right? So you will see that the output voltage is going to be equal to what? The supply's voltage. So if you are to draw the waveform is here already, so I'll just use it. So during the period that the switch is on, the output voltage V naught is equal to the input voltage. So that is why we are saying that V naught during the on time, V naught is equal to V of S. So that is this portion. So when you turn off the switch, you realize that the circuit opens. So when the circuit opens, the V naught is 0. It's not more connected to the supply, so it's going to be 0. So it drops to 0 and stay at 0 till the switch turns on, right? So you have the same pattern repeating. So that is the voltage. So the current too will also take the same pattern. Anytime the switch is closed or the switch is on, current will be flowing, and when the switch is off, the current becomes 0. So these are the two waveforms. So we will be interested in the average value of the output voltage and the RMS value. And I know we know how to calculate them. So you calculate the average area, the area divided by the period. So if you calculate the area of this one, you're going to get VS T on. That will be the area because it's just rectangular. You divide it by the period is T. So this will be the V naught average. So you realize that you have T on over T, which is our duty cycle. So you have the output to be duty cycle times what? The supply voltage, right? Sorry, it's not 8, it's duty cycle. Delta, right? Times the supply voltage. So this will be the output average voltage. Then you come to the current too, and you do the calculation, right? So you see that the average current Q will just be equal to I naught average will be equal to V naught average divided by what? The resistance that you have, right? So this gives us I naught average. So this one is very simple to do, right? So realize that here you are not using there is no freewheeling diode. So this is the operation you are going to have. Please, do you understand? Okay. So the average value is here, the average current is here. So this one is very simple to understand, right? Okay. So if you want to calculate the RMS value of the output, we usually say is the square root of what? The area squared. No, the area squared, you first of all find the square of the area divided by the period and take square root of that. That gives you the RMS value. So we come back to the waveform and look at it. So we come back to the waveform. If you want to calculate the square of the area, you first of all square the VS. So when you square VS, you will get you have VS squared multiplied by T on, right? So we have VS squared multiplied by T on. So this is the average what? This is the square area. So we divide it by the period. Then we take square root of this value. So this gives us V naught RMS. So you realize that T on over T is the duty cycle. So you're going to have duty cycle multiplied by VS squared. So when you simplify this, you should get this expression. So that is the RMS. So you can bring a simple question on this and ask you to do the calculation. So that is this one. And if you want to calculate the output power, you multiply is the RMS value that you use, your RMS of the voltage squared divided by the resistance, or you can choose to use the current to do the calculation. And if you want to know the input resistance, then you can do this calculation. So there are simples. So there is a simple example here. I will skip this one. Then we'll move to the next one. I'm just interested in explaining the diagrams and helping you understand them. So we look at this chopper, which is still step down. So we'll see why it is step down. So this is step down with RLE load. So this RLE load can just represent a DC motor, right? This can represent a DC motor because DC motor has resistance, there is self-inductance, and there is back EMF. So the E here can represent back EMF. So you can just have this as a motor circuit that you are trying to control. But that is not. So let's focus on the analysis. So when you're analyzing power electronic devices, please look at the switches that are on. When this switch is on, what happens? When this switch is on, what happens? What will even cause the switch to be turned on in the first place? So these are the things you look out for. So when you know the switch that is on, you analyze the circuit, get the analyze that one, then you look at the next switch. So let's first of all start with this, the first one. So when the switch is closed, right, we are going to have positive voltage. And sorry, so we have this will be the polarity across the diode. So we have plus, minus across the diode. And you realize that the diode, so this negative voltage will reverse bias the diode. So the diode is not going to conduct. So that means that you have an open circuit here. So this acts as an open circuit. So the current that is coming from the supply will go through the load. So IS, so we draw the waveform. So let me just do that now. So let's first of all look at V naught. So we see that V naught will be equal to what? Vs, right? So we have Vs, V naught will be equal to Vs during the time that the switch is on. So when you turn off the switch, you realize that it will open. So when it opens, what happens? So this is, okay, let me explain the time. I've left out something. During the time that this switch is on, the CH1 is on, the current is flowing through the load, and the load has inductance. So what happens is that the inductance will be storing energy. So it will be storing energy. So it will store energy during the time that the switch is on, right? Please, do we get that? So it will store energy during the time that the switch is on. So when you turn off the switch, and when you turn off the switch, this is what will happen. So we know that the resistor will be absorbing the volts, the power, right? So that is where the power will be dissipated, but the L will store energy. So the energy that is also in turn of the switch, the L will want to, the inductor will want to release the energy that it has stored. So you realize that the current in the inductor, we know the energy in the inductor is given by Li squared. So if energy is reducing, that means that the current too is reducing, because the inductance is a constant. So if it is releasing energy, that means that the current is reducing in magnitude. So you have the voltage of the inductor to reverse its polarity. So this is the voltage across the inductor. So realize that the change in current is now negative. So this voltage is going to be negative. So that is the one that is driving what? That is now acting like the source. So it's producing the current. So because of that, the polarity here, the diode will be forward biased. That is what I want you to understand. So this is what will happen in the diode to be forward biased. So when the diode is forward biased, it will be short circuited, because we are assuming ideal operation. So we are going to have a short circuit here. So this side will be short circuited. And you realize that the load will be disconnected from the supply. So the voltage across the load now becomes zero. So during that time that the diode is conducting, the voltage drops to zero. So the switch turns on again. So when the switch is turned on, the diode will see positive voltage, negative voltage, and turn off. And you have the pattern in that manner. This is the voltage, right? So let's look at the current. So you realize that diode inductor doesn't allow current to change instantaneously. So because of that, the current will be rising up to a maximum till the time that the switch will be turned off, and that current will begin to decrease as the inductor releases the energy that was stored. So the load current will be the same as the inductor's current, because the inductor is part of the load. So I naught will have a waveform similar to the current of the inductor. So which we've seen already, right? So which we've seen already, which is the one here. So realize that we are assuming steady state operation. So don't ask me why it is not starting from zero. We are assuming steady state operation. So it will start from a certain minimum current, increase up to maximum during the time that the switch is on. During that time, the diode, the inductor is storing energy. So when you turn off the switch, it will release that energy. So the current decreases, and you have that same pattern again, right? So this is for the output. So we know the output current waveform. We have the output voltage waveform. Please, do you understand the two? If you want me to go over the operation, let me do, because it's good to understand the operation. If you don't understand the operation, you cannot get these waveforms. Or if you're asked to perform some analysis, some calculations, you might not know which formula to use. Because what if the circuit changes? So you have to analyze and understand what will happen next. Right. Okay, so if there is no question, then
the operation again.
all right. Okay, so first of all, we look at the time that the CH1 is on. So I explained that when it's on, we have positive. Let me use. So we have positive at this side, and then this is negative, right? So diode in this form, the diode is what? Reverse bias, because negative voltage is connected to the anode and positive voltage is connected to the cathode. So it is reverse bias. So it's going to act as an open circuit, right? So you have power flowing from the source to the load. So during that time, so power will be flowing from the source to the load and back to the source. That is what will be happening. So that's how the current will be flowing. So when you apply KVL, you see that V naught be equal to Vs, right? So that's what we are going to have. So when you are drawing the waveform during the time that the switch is on, CH1 is on, you have V naught to be equal to the supply voltage. That is this portion, right? So that is when CH1 is on. So if we turn it off, this is what is going to happen. Okay, I explained that when it's on, currents, this is the power is flowing, right? And when you check the load, there is inductance. So the inductor will be storing the energy. So its current will keep rising as it's storing energy. So the current will be increasing as it stores energy, right? So that is where when you look at the waveform, the current increases during the time that the switch is on. So it's storing energy during that time. So now, when you turn off the switch, the diode, the inductor will want to release that energy that was stored, right? So it will want to release that energy that was stored. So because of that, the energy will be decreasing. So when the energy is decreasing, you realize that the current value will be decreasing. So the current, the change in current is now negative because it's now moving from a higher value to a lower value. So the change in value becomes what? Negative. So when that happens, the polarity of the inductor will flip. So when it flips, it's now acting like a source. So initially, this was if you focus on the inductor alone, you have a polarity like this. So but when the current it begins to release energy, the polarity will flip. So you rather have minus plus. So here will be plus and this side will be minus. So realize that when the diode sees this kind of voltage, it will be forward bias. So it will be conducting. So when it's conducting, it is acting as a short circuit. So the output is shorted from the input. So it's no more connected to the input. So during that period, the diode, the inductor is releasing energy. So the output voltage will be negative, will be zero rather. So that's why during the time that the switch is off, the output voltage is zero. And the current in the inductor will be decreasing. So which is the same current in the what? Which is the same as the load current because they are in series, right? So that is what happens. That is basically how it operates. Have I answered the question?
Yes, please. Thank you very much.
All right, so that's why we are having these two waveforms. So the next thing to do is get the average values. So the average output voltage and average current. So we know that V naught is equal to VR plus VL plus E, right? But we know this. So we calculate the average of this. So the average of this, you know the average value of the average voltage of an inductor over a switching period is zero. So that means that this goes to zero. So we have the average value to be VR plus E. So that is from the diagram, right? So this is from here. So realize this is from here. The voltage drop across the resistor plus the voltage drop across the diode plus E. That is what I've written. So the average value will be equal to this because the average value of an inductor over the voltage of an inductor over a switching period is zero. So we come to the waveform and calculate for V naught. So I think we've seen this waveform a number of times. So V naught average will be duty cycle times what? The supply, right? So this will be the output voltage, that is the average. Then the current average this waveform, we also have seen it. So the average is given by what? So I naught. So I naught average is given by I mean plus I max over 2. So this is what you are going to get. So we know the average output voltage and the average what output current. So that is what you do. I think the this was what I was explaining. The time that the switch is on. So the diode will be open circuited and you have it this way, right? Okay. So that is what we have. When you also look at the time that it is open, you're going to have the diode shorted because it will turn on and then you're going to have it like this. So you can write the equation and then go ahead. So these equations, they are the differential form, but I didn't use that method. So, but he explained in class that whether you use the differential equations or the one we know already, it doesn't really make any difference in the final example, the final value that you arrive at. So you can go through this. I think you've done differential equations, so you can calculate for the current and substitute in the value. So when you do that, you will end up with this. So we just focus on the steady state operation, right? So that is that is how it operates. Please do you understand? Okay, so I will skip the example. Let me see. Okay, so let's solve example on this so that we can understand it better how to go about solving an example. So you just have to. So the thing is you can choose the diagrams, which is good, but always pay attention to what you are given in the question. So he has told you that don't come to the exam hall with your own questions or your own stuff. Just understand and come to the exam hall. So you see that the two circuit that we've analyzed, he can give you something that maybe some of the things might not be there. So just understand how to analyze the circuits. So let's look at this example. So this example says a step down chopper has an inductive load. So this one is an inductive load. So inductive load consists of resistance and then inductance. So that is an inductive load. It's not just only what inductance. Please, I hope this is clear. So the resistance is 1 ohm and then the inductance is 10 millihenry. So the source voltage is 20 volts and the chopper operates at a frequency of 100 Hz with an on time of 5 milliseconds. So we should determine the average load current, the maximum and minimum load current. So that is what the question is asking us to do. So this one is always good to draw the circuit that you are given. So we have a switch. So this is a step down. So we know a step down already. So we have a switch. We have the freewheeling diodes connected this way. Then we are told that the load is what? Inductive. So there is resistance and there is inductance. So you can draw it anyhow. So R, and this is our output V naught, and the input is what? Vs, right? So this is the diagram. So you have to be able to analyze this diagram to get the waveform for the output voltage and then the current waveform. But you see that the waveforms will not change because I think the waveforms will not change. So we still have the same waveforms for the output voltage and then the output current, right? So the duty cycle, the average values will remain the same. Nothing will change. So that is a good thing about this example. Though they've taken the E out, but nothing will not change, right? So now we have to calculate the average load current. So the average load current, so this is I naught, which is the load current. So what we need is to get when we know the average voltage. So the average load current to be equal to the average output voltage divided by what? The resistance, because it's the resistance that actually what dissipates the power. So that is what we are going to get. So we need to get V naught average. So how do we get it? V naught average is what? The duty cycle multiplied by what? The input voltage. So the duty cycle, what is the duty cycle? So we have to check the question. So we've been given the on time as 5 milliseconds and the switching frequency as 100 Hz. So from the switching frequency, we can calculate for the switching period, which is 1 over F. So we have 1 over 100 as your switching period, right? So that is a switching period. So you end up with 0.01 seconds. So you can convert this to milli. So when you convert this to milli, you should get 10 milliseconds. So this is the switching period. So we divide the on time by what? The switching period, which is 5 milliseconds divided by 10 milliseconds. So you get 0.5 as your duty cycle. So 0.5 multiplied by the input voltage, which is 24 volts. So you have 24 volts. So this will give you 12 volts as the average what? Output voltage. So you come and substitute it here. You know your output resistance. So you just come and substitute it. So you have 12 divided by 1 ohms. So that means that the average load current is what? 12 amps. So this is 12 amps, right? So we know this is 12 amps. So the next question we need to answer is the minimum and then the maximum load current. So how do we go about? So we are interested in I minimum and I maximum. So we know the average already. So we know that the I minimum plus I maximum divided by 2 is equal to the average, which is now 12, right? So we need to get another expression that will help us get I minimum, because this is one equation involving 2 variables. So we need to get another one to be able to solve this equation. So how do we get that? So this is where we need to now calculate the change in inductor, the current of the inductor. So the formula he gave you in unit 1, which is change in I is equal to VTA over L. You have to use this formula. So this is where it becomes handy. So you need to calculate the voltage time area divided by the inductance to get the change in what? Inductance current. So the change in inductance current is equal to the maximum current times the minimum current. So when you get this value, you get I max minus I min equal to what? That value. So how do we calculate the voltage time area? So okay. So let me just make you please, can you hear me? And can you see what I'm writing? Hello. All right, so let me just continue. So we know that when you go back to the waveform, the output voltage is equal to VR plus VL, right? So that means that VL will be equal to V naught minus VR, right? So during the time that the switch is on, so this is what we are going to have. So during the time that the switch is on, but we know that the average value, the average V naught is VR, right? So V not average is equal to V. So I think we should also take note of this information. So that means that when we are during the time, let me just draw the waveform like this. So during the time that the switch is on, VL will be equal to V naught minus VR, right? But during the time the switch is on, V naught is Vs. So we are going to have Vs minus V naught average. Please, do you understand this one? Or I should
Can you come again?
so you know you understand this formula, right?
Please.
Okay. So now when you make VL the subject, you get V naught minus VR. But bear in mind, these are not average values. Do you get it? So we need to get during the time that the switch is on, V naught is equal to Vs, right? So V naught is equal to Vs. So we have V naught to be equal to Vs. So wherever we see V naught here, we can put Vs. And VR is also equal to V naught average, because the average output value is equal to VR, right? So that means that we can replace VR with what? V naught average. So that is why during the time that the switch is on, the VL value is what? Vs minus V naught average. So that is during the time that the switch is on. So when the switch is off, we know that V naught is 0, right? So because V naught is 0, you have VL to be equal to minus VR. So it comes into the negative region. So it comes into this region and it stays at what? Minus V naught average, because VR is what? V naught average. So then the waveform, the pattern continues in that manner. So what we need is what? The voltage time area. That is what we need. So you can either use the area, the positive area, or use the negative area. Whichever one you would like to use is up to you. So you can choose to use this one or use this one to get the voltage time area. Please, is that clear? Okay, so now let's which one should we use? Should we use the top one or the bottom one? I want you to decide.
The top.
The top one.
All right. So the top, we know that this time is T on and this is T off, right? So the area is going to be Vs minus V naught mod.
Hello, please, can you go over the graphs, the waveform?
Let's continue. So I was saying that the VT will be equal to Vs minus V naught bar times what? T
Hello,
on,
please,
right? So we get,
can you go over the waveform?
all right. So we have to look at what will be the voltage across the inductor during the time that the switch is on, and what will be the voltage across the inductor during the time the switch is off. So that is the two scenarios. So we know that the output voltage V naught is equal to VR plus VL, right? So that's, we know that. So if we make VL the subject, you will get V naught minus VR, which is the one here. So now we have to look at during the time the switch is on, what is happening. So during the time the switch is on, you know that V naught is equal to the supply voltage, which is Vs, right? Do you get that one?
Yeah.
Okay. So V naught, so wherever you see V naught, we put Vs there. So what is VR? VR, when you find the average of the output, it's equal to what? VR. So we can replace VR with what? The average of the output, and the average of the output is what? V naught bar, right? So that means that the voltage across the inductor will be Vs minus V naught bar, which is the one here during the time that the switch is on. So the magnitude is Vs minus V naught bar. Then when you look at the time that the switch is off, V naught is 0. So because V naught is 0, you have VL to be equal to negative VR. But we know that VR is already what? V naught prime. That is the average of the output. So it will come into the negative region, then it will stay at minus V naught bar. So the switch turns on and the waveform repeats itself. Do you get it? So if you are calculating for your VTA, you can either use the top one or the bottom one. So we are using the top one. So we need to find the area of this. So which is
I have a
Vs
question.
minus V naught bar multiplied by T on. So that gives us the voltage time area. So we can put in values and get. So the supply is 24. Yes.
Said that the when the switch is on, the output, the average of the voltage across R is equal to the output voltage. The average output voltage.
Yes, that is yes.
Yes. But
Yes, that
the
is it.
but the resistor, sorry, the inductor too is there. So why not the sum of the average voltages across both? That will give us the output.
But we know that we know the average value of the average voltage of the inductor is 0. So that means that the average of the output will be equal to the voltage across the resistor. So
Oh,
that is why I'm
okay.
saying that V naught average is equal to VR.
Thank you. I forgot about that.
All right, you're welcome. So let's substitute in the value. So we will have 24 minus 12 because 12 is the average output. Multiply by the T on. T on is 5 milliseconds. So 5 times 10 exponents minus 3. So this is the VT. So we need to divide this by the inductance. And the inductance is giving us 10 millihenry. So the change in IL will be equal to this. So we know that we have 12 times 5 times 10 exponent minus 3 divided by 10 times 10 exponent minus 3. Good. So that is what we are going to have. So you can simplify this. So that will be 60 over 10, right? So you will get 6 amps. So the change in the inductors current is 6 amps. Please, do you understand how we got here? So now that we know that, then we come back and then do the calculation. So we get the other equation. So change in IL is equal to T I max minus what? I min. So which is equal to 6 amps. So this is 12 amps. So you can get two equations, solve them simultaneously to get your minimum and then the maximum current. So here you have I min plus I max to be equal to 24. All right. So that is what you're going to get. So you have two equations, so you can solve them simultaneously. Your calculator can do it easily, right? But the I max, I think I max should be This plus this divided by 2. I believe. So that will be 24 plus 6/2. I think you should be getting something like this. So that will be 15 arms, right? So the maximum is 15 arms, and the minimum will be 9 arms, I think. So confirm for me. So let's go through the solution together. So you all understand how we arrive at this, the average, how we calculated for this, how we calculated for the switching period, the duty cycle, the average value, and then the average volt output voltage and average current. Then we come here and then do the same calculation. So this is the waveform that I just explained. So here the V naught is referring to the average output, right? Okay. So we've done the calculation already. So this slide is just explaining this waveform. So this one, yeah, gives us this portion one. This one gives us to get 6 arms. We know this one. You solve the two simultaneously, and you end with 9 arms and then 50 arms. Okay, so I think we've exceeded the time. So if you have any question, please ask so that I'll explain. Whether it's from the previous material we covered, the switches, thermal modeling, or what we are doing currently, the step down choppers. So you have any question on this, please kindly let me know so that I will explain. Please, is there any question? Okay, if there is no question, we'll end here, and God willing, next week we will continue. So that one will just focus on solving examples so that you can prepare well for your midterm. So please let me know where your midterm will be up to so that I can get questions up to that area so that we just focus on solving examples for your midterm. So if there is no question, then we will end here and continue another time. Thank you.
Thank
All
you
right, thank
too.
you too.